Alright guys, how's it going? Today we're going to talk about rate of reaction. Now when we conduct an experiment, sometimes you can measure how fast it's reacting, how fast it's getting from the reactants to the products. Now, let's take for example, we have a conical flask, a reaction vessel, and we place it on a measuring scale, an electronic scale. We tear it to zero, and when we add up reactants, our beginning substances at the top, and put it in there. And then you're going to have a readout in mass, all right? And then once the reaction starts, maybe gas will be given off. We don't know, right? And you can see that the mass readings changed. Usually it will decrease because of that. And you can plot them in terms of time versus mass. But there is another way to do it. For example, if gases are being released from the reaction, you can put a cork stopper and also a glass tube into the cork stopper, and you can collect the gas with a syringe, because what will happen is the gas will come out and then push its way through into the syringe. Alright? And the syringe is going to, the tip of the syringe, the plunger I guess is what you can call it, the plunger will move outwards as volumes of gases get collected in here. And then you can record it in very discrete time intervals. And when you collect all your data, you can plot them in this table down here. You can see this table here, from time 0 all the way to whatever. Here, I'm just making things up, is in 30-second time intervals. And the volume, I made this up as well, actually copied from the book, the volumes of gas collected. Alright? And what you're going to do is that you're going to plot it onto a graph as indicated by the X mark. And then you're going to draw a best fit curve line from 0 all the way to the end. And what can you see from this graph? Apart from this outlier here, which we did not fit into the graph, because a graph should be a smooth curve. So if you draw something that's not so smooth like that, kink, that's not a smooth curve and that's not a real graph. So there would be a problem with this data collection, and it could amount to several reasons. Okay? Alright, come back to the top. Plot the curve, and this is what we see. What can you tell is going on in this particular reaction? And in most cases, all reactions will behave the same way. We can see that the X versus Y, the rate of increment, or the rate here is really sharp. It's going really sharp outwards. Alright? And as you add more time to it, it's slowly decreasing in its rate of change. And as you get to the top, it's going to be at a constant flat line. What does this tell us? This tells us for all reactions, at the very beginning of the reaction, a lot of this substance or reactants will react. And a lot of reactants will turn into products very quickly. And as you go, and as the reaction continues, what you're going to notice is as less and less reactants becomes available, the rate of reaction is going to decrease until you reach to the end where you do not have any more available reactants, or one of the reactants finished before the other, and so no new products can be made. And what you're going to see is that this is going to happen as the reaction ends. No more new products are collected. And this is the general graph that most rate of reactions will go through the same pattern as I've drawn. So here is a nice little graph that an illustration that I can use to describe what is happening. At the beginning of the reaction, you will see lots of substance, which has the green reactant, whereas the pink reactant. And they're going to collide, all right? So they're going to collide. Some are not going to collide, some are going to float elsewhere, some are going to collide, okay? Not all are going to react with each other, well, that's fine. Some are going to collide. There you go, all right? And when they collide, they form a new product. All right? And that's why there's a lot of them available. There's a lot of random collisions going on. With some, like this little reactant is going to hit the reaction vessel wall and stuff like that. Okay? But because there's so many of these reactants, the chances of successful collisions is very high. But towards the end of the reaction, you will see very few reactants, because remember we said that this reactant, the product of this reaction is given off as gases. So when you have successful reactions, they're going to become gas and it's going to float from up here all the way into the sewage. And so what you're left with is less amounts of reactants. And the number of successful collisions will ultimately go down. Okay? So you only end up with less successful collisions, which means less successful products are made. So that is it. Next class, we're going to talk about factors that may affect the rate of reaction.